As our very smart friend here informs us, the history of magnetism begins thousands of years ago with the ancient civilizations in Asia Minor in a region called Magnesia, where rocks called lodestones, were found that could attract each other. These rocks were called magnets after their place of discovery. In this first video in our two-part series on magnetism, we'll start by taking a look at the properties of permanent magnets, a topic that you're most likely somewhat familiar with just from your experience dealing with permanent magnets in everyday life. And from there, we'll turn to the topic of magnetic fields and how magnetism is created in the first place. We'll end this lesson with a discussion of the magnetic properties of matter, developing a classification scheme for how to classify materials according to their magnetic properties. During this discussion, we'll find out how permanent magnets are actually made. In order to make measurements of magnetic properties, the ancients developed a very simple device called a compass. By definition, a compass is simply a tiny magnet that is free to rotate about a pivot point. And as you look at some of the examples of compasses illustrated in this slide, you can easily see that the needle of the compass is really nothing more than a tiny magnet that is free to spin in a complete circle. Most everyone has had the opportunity to play with permanent magnets at various points in their life, whether these magnets were located on a refrigerator, a garage tool, or even perhaps a game. All permanent magnets possess two magnetic poles, a north pole and a south pole. The magnetic pole, by definition, is a region in a magnet, usually at the end or the face of the magnet, where the magnetic force is strongest. Now, to define the magnetic north pole and the magnetic south pole, we would say that the north pole of the magnet, sometimes called the north-seeking pole, is that magnetic pole which points geographically northward when freely suspended. And given that, you might imagine that the south pole of the magnet, sometimes called the south-seeking pole, is the magnetic pole of the magnet which points geographically southward when freely suspended. Now remember that a compass needle is nothing more than a magnet, that is free to rotate. We can think of the needle of the compass as being freely suspended. So if I were to put a compass on the earth, and I realize it's a rather large one, but that's so you can see it, notice that the red portion of the compass needle points geographically northward. Therefore, the red portion of that compass needle would represent the north pole of the magnet. Remember that the compass needle itself is nothing more than a magnet. Whereas the blue end of the compass needle points geographically southward, that would be the south pole or south-seeking pole of the magnet. Before we get to the next topic in your notes, that is the difference between geographic poles and magnetic poles, we're going to quickly review the magnetic force rules, which I think you'll probably already be familiar with. So let's take a look at all the possibilities here. If I were to take the south pole of a magnet and bring it near the north pole of a second magnet, these magnets would attract, as I'm showing you with these purple force vectors here. If I were to bring the south pole of a magnet near another south pole of a second magnet, then those magnets would repel each other, as I'm showing you with these force vectors. Likewise, if I were to bring the north pole of a magnet near the north pole of a second magnet, we would also get magnetic repulsion. So we can state these force rules rather succinctly as follows. We can simply say that opposite poles attract, like poles repel. Notice a similarity with charges, right? We had a similar set of force rules for electric charges, that opposite charges attracted each other, like charges repelled each other. Okay, so the same rule really applies to magnetic poles as it does the electric charges. Here's a nice little simulation or animated GIF that will help you visualize the situation. Okay, notice that it is really doing nothing more than giving you a visualization of these force rules. Now that we've reviewed the force rules for magnetic poles, we'll return to the topic of distinguishing between geographic poles and magnetic poles. Let me just start by saying that it's important to distinguish between a geographic North Pole and a magnetic North Pole. Okay, there is clearly a difference. Now, the geographic poles are defined by the axis about which our Earth spins. Okay, that's what I'm trying to show you here in this picture. And if you look at where my laser pointer is located right now, okay, it is located near the geographic North Pole of the Earth as defined by, okay, the North Polar Axis. So this is how our geographic poles are defined. As we've already stated in a previous slide, okay, we said that if we were to place a tiny compass needle on the Earth, okay, and remembering that a compass needle is really nothing more than a tiny magnet that is free to rotate, okay, free to spin about its axis, then the North Pole of the compass needle is, by definition, the one that points geographically northward, okay, as I'm showing you here. Points, that is, towards the geographic North Pole of the Earth as defined by the polar axis, okay, as I'm showing you in this illustration on the slide. But that kind of begs the question, why would a compass needle point geographically northward? Okay, well, only because it interacts with the magnetic field of the Earth. Okay, but given what we know about the force rules, okay, we know that the north magnetic pole of the compass needle must be attracted to a south magnetic pole, in which case we can infer that a south magnetic pole must be located, okay, somewhere near the geographic North Pole of the Earth. Okay, opposite poles attract. So if we can imagine that there is a bar magnet on the interior of the Earth, and we'll talk more about this later, okay, it turns out that the magnetic field of the Earth is very similar to what we would get if you can imagine this huge bar magnet, okay, placed inside the Earth with a south magnetic pole located near the north geographic pole. Okay, hopefully you can see then that this is the only reason that a tiny compass needle, a tiny magnet would point northward, okay, because the north magnetic pole of the compass needle would be attracted to the south magnetic pole of the Earth. And that south magnetic pole of the Earth is located near the geographic North Pole of the Earth. It turns out that Earth's geographic poles, which are aligned with Earth's rotation axis, okay, are not in alignment with, okay, are not located in the same place as Earth's magnetic poles. This is the phenomenon known as magnetic declination. And let me try to show you with this simulation. Here we have our spinning Earth, and the geographic poles are, okay, defined in relation to the Earth's rotation axis. When we look at the magnetic field created by the Earth, okay, and like we said in the previous slide, if we imagine that there's a huge bar magnet in the interior of the Earth, okay, it turns out that, okay, the axis defining this magnetic field here is not in perfect alignment with the axis which defines the Earth's rotation. Okay, this is what we mean by magnetic declination. It turns out that the geographic poles are about 1,800 kilometers, okay, from Earth's magnetic poles. Earth's magnetic south pole, which we said is near Earth's geographic North Pole, okay, is currently located in the Hudson Bay region of northern Canada, okay, not where Santa Claus lives. We've already seen that magnetic poles have some things in common with electric charges, but there are some important differences as well. In this slide, we'll compare and contrast these two phenomena. Okay, starting with the similarities between electric charges and magnetic poles. Well, as we said previously, we know that in the case of electric charges, like charges repel while opposite charges attract. Okay, we have a similar rule for magnetic poles, that like poles repel while opposite poles attract. When it comes to describing the strength of the force between electric charges and magnetic poles, well, we know that to describe the force between electric charges, we have Coulomb's law, which takes on this form. And we see here that Coulomb's law is an inverse square law. That as two charges get further apart, okay, the force between these two charges gets weaker with the square of the distance between them. So we call it an inverse square law. Force gets weaker as the square of the distance. A similar rule can be applied to the case for magnetic poles. When we're talking about permanent magnets, okay, we can say that the magnetic force between two poles of two permanent magnets goes like a proportionality constant times the product of the pole strength of each magnet, okay, divided by the separation distance squared. So we see here that in the case of magnetic poles, okay, the magnetic force also gets weaker with the square of the distance between those two poles. So as we can see, there is certainly a lot in common between electric charges and magnetic poles. Okay, but here is the key, very important difference between them. For the case of electric charges can be isolated. That is, single charges exist. You can isolate a single electron or a single proton in nature. Okay, you do not have to say that, oh, in order to have an electron, you must have a proton too. No, you can have a single charge in nature by itself. The same cannot be said for magnetic poles. Okay, magnetic poles cannot be isolated. In other words, even at the smallest level of the atom, when you look at the case of magnetic poles, if you have a north magnetic pole, you must have a south magnetic pole as well. You cannot isolate a north pole from a south pole. They always occur in pairs. In other words, I mean, one of the ways this is stated is that magnetic monopoles or single poles do not exist. Even at the smallest level of the atom, okay, when you look at a very, very tiny magnetic field created by, as we'll see, let's say a single spinning electron, you would have both a north pole and a south pole. We'll now shift our focus to a very abstract yet very important concept. That is the concept of the magnetic field. While a magnetic field is a physical quantity, okay, it occupies space and possesses energy, it is not something that can be seen, so it is difficult to represent with a picture. Okay, but we can think of a magnetic field as a region in space surrounding a magnetic source where the magnetic force can act. And we'll look at various examples of magnetic sources, okay, in a bit. Okay, when we look at the cause of magnetic fields, and this is by far the most important thing that I'll say in this entire lecture that you should know about. When we look at the cause of magnetic fields, in all cases, whether we're talking about the magnetic field created by a permanent magnet, a current-carrying wire, or the magnetic field created by a planet like the Earth itself, in all cases, magnetic fields are created by moving electric charges. So we know that stationary electric charges create electric fields, okay, giving rise to electrical phenomena. But when you get those charges to move, in addition to the electric field they create, a magnetic field is created as well. So it's important to realize that the source of magnetism is also the source of all electrical phenomena as well. Okay, that is electric charges. So if all magnetic fields are created by moving electric charges, let's take a look at some common sources of magnetic fields and see where these moving electric charges are, starting with the case of current-carrying wires. Now, it turns out that in 1820, a Danish high school science teacher by the name of Hans Christian Ørsted accidentally discovered the relationship between electric charge and magnetism. Okay, while the phenomenon of magnetism had been known for thousands of years, and I alluded to this in a previous slide, an understanding of what caused it was not known until about 200 years ago. So in Ørsted's laboratory, he noticed that the needle of the compass was deflected when an electric current existed in a wire that he connected to a battery. And he reasoned that this would only happen if the moving electric charges in the wire could create a magnetic field, okay, for the compass needle to interact with. So I will try to demonstrate this simple experiment, okay, the one that Ørsted conducted some 200 years ago. I'll try to demonstrate this for you in the next slide.
By the 1800s, the phenomenon of magnetism had been known for thousands of years, but it wasn't until 1820 that the cause of magnetism was discovered by chance. In 1820, a Danish high school science teacher named Hans Christian Ørsted just happened to notice that when a compass was placed near a current-carrying wire, it was deflected. So we're going to repeat Ørsted's experiment here. I've got a compass. I'm going to place it near this wire, and we're going to see that when a current is flowing through the wire, when I turn on the power supply, we will see the deflection of that compass needle. So let me turn on the supply and let's see what happens, just as Ørsted discovered a couple hundred years ago. We see then that the cause of magnetism is moving electric charges, in this case a current in a wire.
For the case of current-carrying wires, the source of the moving electric charges is pretty obvious. But what about the case for permanent magnets? Okay, where are the electric charges there? Well, to see where the moving electric charges are, we have to go down to the level of the atoms themselves. Okay, now we know that all materials are composed of atoms and that all atoms are themselves composed of charged particles, that is protons and electrons. It turns out that the electrons, okay, not the protons, it's the electrons in the atoms that are the major contributor to the magnetic field. Now, there are really two different types of electron motion that contribute to the magnetic field. The first is the orbital motion of the electron about the nucleus, while the second is a property that we call electron spin. A nice analogy to understand this is to consider the motion of the Earth about the sun. Okay, and you well know that as the Earth makes that elliptical, okay, nearly circular orbit about the sun that takes about a year, okay, this is what we would call the orbital motion of the Earth. And this motion is analogous to the orbital motion of the electron as it moves about the nucleus. Okay, the Earth also spins about its own axis as, okay, it orbits the sun, okay, making one complete spin in a day. This rotation of the Earth about its own axis is analogous to the spin of the electron, okay, as it orbits the nucleus. Now, while this analogy may be useful and may actually help you remember these two types of electron motion, it turns out that electrons don't really spin about their own axis. This property of electrons that we call spin is actually quite a bit more complicated. Okay, but the analogy is a good one to kind of help you remember that there are two types of motion. So, it turns out that the major contributor to the magnetic field in a permanent magnet, it's the spin of the electron. It's the electron spin that is way more important than the orbital motion of the electron. So, okay, given that electrons possess this property we call spin, each atom really behaves as a little tiny magnet producing a tiny magnetic field. Remember, all atoms consist of electrons. Now, it turns out that when electrons in an atom and neighboring atoms are spinning in the same direction, okay, and that's what I'm showing you with this animated GIF here on the right-hand portion of your screen, okay, that there's a spin up and spin down. And when electrons are spinning in the same direction, then the little tiny magnetic fields that they create add to form a stronger magnetic field. But when you get electrons spinning in opposite directions, okay, then the magnetic fields cancel. It turns out that in permanent magnets, there are lots of electrons that are spinning in the same direction. Okay, therefore, these electrons spinning in the same direction, they're very tiny magnetic fields add up to give you a noticeable magnetic field. Okay, so this is the source in atoms like iron, okay, ferromagnetic materials, we'll talk about this a little bit later. You get a lot of electrons spinning in the same direction, in which case the magnetic field is noticeable. Lastly, we'll talk about the magnetic field of the Earth. Now, you remember we alluded to on a previous slide, we said that the magnetic field of the Earth resembles that of a huge bar magnet, okay, located inside the Earth. Well, where are the moving electric charges in this case? While it is true that the cause of the magnetic field is not really all that well understood by geologists, okay, most geologists believe that it's really a combination of, first of all, the convection currents deep within the molten part of the Earth, okay, combined with the Earth's rotation that causes circulating electric currents. So the molten part of the Earth, it contains a lot of iron atoms. It's mostly iron. And because it's molten, those atoms and the electrons in the iron atoms are free to move. So the convection currents get those electrons in those iron atoms moving in addition to the rotation of the Earth. Okay, so these two motions get the electrons to be moving, okay, to be rotating, in which case they produce a weak yet noticeable magnetic field. We've said that the magnetic field is a region in space surrounding a magnetic source where a magnetic force can act. We've also said that the source of all magnetic fields, okay, is moving electric charges. We now ask the question, how is the direction of the magnetic field determined? Well, by convention, okay, physicists agree that the direction of the magnetic field at any point in space, okay, is the direction that the north pole of a compass needle points at that point in space. So, for example, you see illustrated in this slide a permanent magnet. If I want to find the direction of the magnetic field, let's say at this little point in space I'm showing you here, well, what would I do? Okay, I would now take a compass and I would place the compass at that point in space, and as we're saying by this convention, okay, the direction that the north pole of the compass needle points at that point in space is the direction of the magnetic field there. So let me remember the direction that the north pole of the compass needle points. Okay, let's draw in the magnetic field vector at that point. Okay, same direction as the direction that the north pole of the compass needle points. Okay, I now have the direction of the magnetic field at that point in space. Now, obviously, this is simply the direction at that one point in space, but I could do this at multiple points in space to see what the magnetic field pattern looks like around a magnetic source like this permanent magnet.
Now, as we've said previously, the concept of a magnetic field is very abstract. I mean, you can't see magnetic fields, you can't touch them, they're really intangible. So, physicists develop a model, a concept called magnetic field lines, sometimes called lines of force, which help them deal with this abstract concept. Magnetic field lines are simply imaginary lines that show you the shape of a magnetic field around some sort of magnetic source. So for example, in this permanent horseshoe magnet you see here, I could draw some magnetic field lines which show you something about the shape of the magnetic field in that region. Now, some properties of these field lines. First of all, the direction of the field lines in space, they go from the north magnetic pole to the south magnetic pole. That's just a convention. If you want to find the direction of the magnetic field in space, well, you can determine this from the field line itself. A magnetic field will always be tangent to or parallel to a field line at any point. So for example, if I want to find the direction of the magnetic field at this point in space where you see the little black dot, I will then draw in a tangent line, a line that is tangent to that magnetic field line at that point, and that vector, the magnetic field vector, which goes from north to south, will show me the direction of the magnetic field at any point in space. Something else we can tell about field lines, something else that this model will tell us, and that is related to the field line density. That is how close the field lines are together. So it turns out that in regions where the magnetic field lines are close together, this is a region where the magnetic field is strong. So for example, this region in the black circle, these field lines are pretty close together. That tells us that the field is strong there. Notice that that region is pretty close to a magnetic pole. If I look at the second region over here, look how far apart those field lines are from each other. That suggests a region where the magnetic field is weak.
So we've said that there are regions in space, okay, where the magnetic field is strong and other regions where the magnetic field is weak. Magnetic field strength is thus a new physical quantity. Now, there are models that will allow physicists to predict the strength of a magnetic field around a magnetic source. In the same way, we have a model, for example, Coulomb's law, to predict the strength of a force between two charged objects. Okay, but I will say here that the model that is used, something called the Biot-Savart law, is kind of beyond the scope of this course. So predicting magnetic field strengths is not something that we're going to be doing here. But the quantity magnetic field strength does have a unit that you need to recognize. Okay, with every new physical quantity comes a new physical unit. So it turns out that the SI unit for magnetic field strength is the Tesla. There's another unit which you should recognize, a much less commonly used unit called the Gauss. And this is in the Gaussian unit system. It turns out that a Tesla is a rather large unit of a magnetic field. That 1 Tesla is equal to 10,000 Gauss. So when you talk about very weak magnetic fields, like for example the magnetic field of the Earth, the Gaussian unit is a pretty good unit to measure that. When you talk about the magnetic fields created by very powerful electromagnets, however, okay, the Tesla is a better unit to measure large magnetic field strengths. As I said on the previous slide, we will not use any kind of mathematical model to predict the shape of a magnetic field around a magnetic source, but we will nonetheless, okay, state what these magnetic fields look like for various magnetic sources, starting with the important case of the bar magnet. So for the bar magnet, I'm showing you what the magnetic field lines, what the lines of force look like in space surrounding that bar magnet. First, I want you to notice that, okay, the magnetic field lines have direction. Okay, that the magnetic field lines, as we said in the previous slide, always point from the north magnetic pole towards the south magnetic pole in space. In order to save space, you'll notice here that sometimes not the entire magnetic field line is drawn. For example, if you follow my laser pointer here, you see that the direction of this magnetic field line is given here, but the field line just ends because we ran out of paper and it picks up over here. So you have to kind of imagine that this forms a closed continuous loop. It's simply that not all of it is drawn. So for example, this magnetic field line over here would come over and, okay, pick up over here on this part of the page, okay, where we left off. Secondly, I want you to notice that the magnetic field lines are much more crowded at the poles of the magnet. Remember we said that the field line density, that is when the magnetic field lines are very close together, like if you look in this region here, that suggests the magnetic field is strong. When we look at the magnetic field in this region, however, you'll see that they're not very crowded. The field line density is much smaller, suggesting the magnetic field is much weaker there. All right, and thirdly, I want you to notice here when I point out in this illustration here, okay, that magnetic field lines form closed continuous loops. Okay, they continue inside of the magnet as well. Now, very often the continuation of the magnetic field lines is not shown inside the magnetic source, but I'm showing it to you in this diagram here because I want you to realize that magnetic field lines have no definite beginnings or endings. They always form closed continuous paths. This makes the magnetic field very different from the electric field. Okay, electric fields begin and end on electric charges. They have definite beginnings and endings. Magnetic fields do not. Remember we said previously today that you can isolate a single electric charge. And in that case, the electric field line begins on that single electric charge and can extend outward in space. Since you cannot isolate a single magnetic pole, okay, they always come in pairs. You always have a north pole and south pole. This is why these magnetic field lines form closed continuous loops. They do not have any beginnings or endings. Okay, they do not start and end at the poles. Okay, these closed continuous loops will create both a north pole and a south pole.
Now, surrounding every source of magnetism is a magnetic field. This magnetic field permeates all of space, and you can't actually see it, but what we're gonna do is we're going to do something to notice the effects of the magnetic field. Now, the magnetic source we're going to take a look at here is a permanent bar magnet here. And to be able to see the magnetic field pattern surrounding this bar magnet, I'm going to stick a piece of white paper on top of it. And I've got the picture of the magnet drawn in there. And I'm then going to take this transparency, place it over that, and we're going to sprinkle some iron filings on here. Now, you'll notice that You can't see the magnetic field, but these iron filings are feeling the effect of the force of the magnetic field. And there's a certain magnetic field pattern that's being produced. In regions where these iron filings are close together, this suggests the magnetic field is strong in that region. And in regions where the iron filings are further apart, in that region, the magnetic field is much weaker. So you'll notice here that near the poles of the magnet, the north and south poles, the iron filings are quite close together, suggesting the magnetic field is very strong there. And in regions sort of in the middle of the bar magnet, the iron filings are more spread apart, suggesting the magnetic field is weaker there. So once again, surrounding every source of magnetism, in this case a permanent magnet, is a magnetic field that permeates all of space. Where the magnetic field lines are close together, the magnetic field is strong there, and where they are further apart, the magnetic field is weaker.
So what would happen if I took a bar magnet and bent it into the shape of a horseshoe? Well, I'd have a horseshoe magnet. Let's take a look at the magnetic field lines for such a magnet. Notice once again that the field lines in space, that is outside of the metallic portion of the magnet itself, okay, are always directed from the north magnetic pole towards the south magnetic pole. Okay, you'll notice here that in this diagram, the field lines which are continuous, and I'm showing you the more realistic case here, you'll notice that any magnetic field line has no definite beginnings or endings, right? That they always form closed continuous loops. Okay, this is the more realistic picture over here, even though this picture on the left is what you would typically see in the text. The magnetic field lines are usually not continued inside the magnet itself. So for example, if I trace a field line here from the North Pole to the South Pole, usually the continuation of that field line in the magnet itself is omitted. Likewise, for lack of space, the field lines are, not always shown to be continuous here. They do stop and end, okay, which is really a misrepresentation of this idea that field lines always form closed loops. They're always continuous. So let me ask this question here. Why are the magnetic field lines closer together for the horseshoe magnet than for the bar magnet? Okay, well, the effect of bending that bar magnet into the shape of a horseshoe not only brings the magnetic poles closer together, okay, it also brings the field lines closer together as well, increasing the magnetic field, okay, in the region between the poles. So this is the reason for the horseshoe magnet. Okay, you can create a much stronger magnetic field in the region between the poles by bringing those poles closer together. So realize that that horseshoe magnet started out as a bar magnet, okay, was bent into the shape of a horseshoe, bringing the poles much closer together in this form, in this shape, than they would be in the case of the bar magnet, making for a more intense, a stronger magnetic field in this region between the poles. So what about the magnetic field of the Earth? Okay, the Earth is pretty important to us, as well as this magnetic field. Well, as we said in previous slides, the magnetic field of the Earth, okay, resembles, okay, the magnetic field surrounding a huge bar magnet. It's as if a bar magnet was placed inside of the Earth. And if you look at the magnetic field lines, as you see in this illustration here, it resembles that of a big bar magnet. It turns out that the Earth's magnetic field is not stable. Okay, there's been more than 20 reversals of the magnetic poles, okay, in the last 5 million years. So the magnetic field of the Earth is changing continuously. It doesn't change that quickly, so it's not going to change a noticeable amount in your lifetime. But like we said, if you could live for 5 million years, you would notice that the polarity of the Earth's magnetic field has switched about 20 times. So what would happen if we bring two bar magnets together? Well, in this first case, notice that we bring opposite poles near each other. And what I'm showing you in the drawing is the magnetic field lines for each bar magnet drawn separately. And what you should notice is that the magnetic field, it's a vector field. So if we ask the question, what does the magnetic field look like in the region between the two bar magnets, we need to add up these two magnetic fields, okay, to find what the resultant or total field looks like. Okay, well, you'll notice here that in the region between the two poles here, that notice that the magnetic field lines exist in the same direction. Okay, for the magnet on the right, the magnetic field in this region points to the left, and for the magnet on the left, the magnetic field also points to the left. Okay, this suggests that the magnetic fields for each magnet separately will add to form a stronger magnetic field in that region. Okay, you'll notice that when we bring two like poles together, in this case two south poles together, we have the opposite effect happening. Okay, you'll notice that here, okay, the magnetic field of the magnet on the right points to the right, whereas the magnetic field of the magnet on the left points to the left. In this case, the magnetic field vectors cancel, suggesting that the magnetic field in this region is weak, okay, close to zero. So here's a case where the magnetic field, it is a vector field, and to find out what the net or total field looks like, we have to be able to add vectors, okay, to add field vectors for each of the magnets separately. Thus far, we've looked at the shape of the magnetic field surrounding permanent magnets, drawing the magnetic field lines for various types and configurations of permanent magnets. But what about for the case of current-carrying wires? We know that current-carrying wires also involve moving electric charges, and thus will give rise to magnetic fields. Well, what do the magnetic field lines look like surrounding various shapes of current-carrying wires? Okay, we'll start out simple, okay, by taking a look at the case of a straight current-carrying wire. And we see here that the magnetic field lines form concentric circles about the wire, as you see illustrated here. Remember, we said that for the case of permanent magnets, the magnetic field lines always form closed continuous loops. That is, they had no beginnings or endings. Well, the same is true for the current-carrying wires. If we want to talk about the direction of the magnetic field, this gives rise to a rule that we call the right-hand current rule. So the rule goes something like this. If you grasp the wire with the fingers of your right hand and let the thumb point in the direction of the current, okay, really the conventional current, your fingers will naturally curl around the wire in the direction of the magnetic field lines. So take a second and make sure that you agree with how this rule is applied to the wire I'm showing you in the figure right here. Okay, you see the right hand, you see the thumb pointing in the direction of the current. Notice how the fingers of the right hand curl in the direction of the magnetic field lines. If I show you this example over here, you see that in the diagram on the left, when the current is upwards, okay, then when you follow this rule, your thumb points upwards and your fingers will encircle the wire in the direction shown, whereas for the picture on the right, when the current is in the opposite direction, okay, the direction of these magnetic field lines will also be in the opposite direction. So I will try to demonstrate, okay, the fact that current-carrying wires produce magnetic fields in the next slide.
So now we're going to take a look at magnetic field patterns surrounding current carrying wires. So in the first case we're going to look at this straight wire which is coming into and out of this plexiglass plane. And what I've done, rather than use iron filings, I've placed some compasses around this wire. And notice right now there's no current in the wire, so these compasses point in a north-south direction, in this direction. In a second I'm going to turn on the power supply. We're going to get a large current through the wire, and you're going to notice that these compasses will align themselves with the magnetic field produced by the current carrying wire. So here goes. On the count of three, take a look at the compasses and we'll see what happens. Okay, if you'll notice here, these compasses show the direction of the magnetic field lines. And you see how if I take my pen and trace around them, they form a circular ring around this wire. This is characteristic of the magnetic field pattern around a current carrying wire. The magnetic field lines form concentric circles.
We've looked at the shape of the magnetic field surrounding a straight current carrying wire, and we see that we get these concentric circles. So what happens when you take that straight wire and you bend it into the shape of a circular loop? What can we say about the magnetic field? Okay, well, when the straight current carrying wire is bent into the shape of the loop, the magnetic field lines become crowded inside of the loop, okay, as this picture will illustrate. And we know that this is a basic property of magnetic field lines, that where magnetic field lines are crowded, that is where they're close together, the field line density is high. This suggests a strong magnetic field in that region. So the overall effect of bending that straight current carrying wire into the shape of a loop is to cause the crowding of the magnetic field lines, okay, which ultimately means that you create a very strong magnetic field in the interior of that loop. Now I'm going to try to demonstrate this for you. In the first demonstration I will simply show you, okay, that a magnetic field exists on the interior of a current carrying loop. Okay, but then I'm going to show you a measurement of the magnetic field, okay, for the current carrying loop compared to the straight current carrying wire. Now I'll admit that this demonstration was actually made for a different class, for Physics 103. So when I mention the calculation of the magnetic field using the Biot-Savart law, don't worry, okay, you did not miss anything. This is not something we talked about in this course, so you certainly don't have to know anything about the Biot-Savart law. But like I said, the Biot-Savart law, it's a mathematical model that you can use to actually predict what the strength of a magnetic field will be at a certain point in space. You don't have to know that even though it's included in the demo. But what you will see, you will see the effect, okay, of how bending a straight current carrying wire into a loop actually causes the magnetic field strength to increase by a factor of about pi.
We're now going to take a look at the magnetic field lines set up inside a current carrying loop. Now you recall that for the straight current carrying conductor, we saw that the magnetic field formed concentric circles around that conductor. If we take that straight conductor and now bend it into a loop, we see that those magnetic field lines get crowded in the interior of the loop, suggesting that the magnetic field in that region is quite strong. So notice with our loop here, we have our compasses aligned with the external magnetic field of the Earth because we have no current in the coil, in the loop yet. But once I turn on the power supply and create a current inside that loop, notice the compass in the interior of the loop, it will react quite strongly to that very strong magnetic field there. So let me turn on the power supply, and here it goes. Okay, we see how intense the magnetic field is on the interior of that loop compared with the magnetic field on the exterior of the loop. In this demonstration, we're going to compare the magnetic field created by a straight current-carrying wire, okay, to the magnetic field that you would get at the interior, the center of a current-carrying loop. Now remember, we said that the effect of taking a straight wire and to bend it into a loop, okay, one that carries a current that is to crowd the magnetic field lines in the interior of the loop. And we showed that in theory, using the Biot-Savart law, that when you take that straight wire and you bend it into a loop of radius r, that the magnetic field, a radius r away from the straight wire, gets increased by a factor of pi, 3.14, okay, once you bend that wire into a loop. Okay, in other words, the magnetic field at the interior of the loop, at the center of the loop, should be 3.14 times as big, okay, as the magnetic field the distance r away for the straight wire. So what you see here is you see a current-carrying straight wire. Okay, I've got our power supply on, and I've got a magnetic field sensor, and we are going to, I've kept this loop here just so we can see the radius of it, and we're going to measure the magnetic field at the loop radius r away from the current carrying wire. So here it looks like we have a magnetic field of about 0.05 milliteslas, okay, due to that straight current carrying wire. Now we're going to measure the magnetic field at the interior of the current carrying loop. So let me turn on the power supply and generate a current here. Okay, and we see that it is about 0.16, okay, about 0.16 millitesla, which when you do your calculation, okay, 0.05 times 3.14 does give you a value of about 0.16 millitesla. So it looks like the theory using the Biot-Savart law works.
Let's take this idea one step further. We've just seen that by taking a straight wire and bending it into a loop, the magnetic field gets about 3 times stronger in the interior of the loop. Well, what would happen if you have not just one loop, but a whole series of loops, okay, like a coil of wire, for example? Well, now you're talking about an electronic device called a solenoid, sometimes called a solenoid coil. Okay, so a solenoid is simply a coil of wire consisting of many current-carrying loops. And you'll see here in these two figures, okay, the magnetic field lines that exist, okay, surrounding that solenoid. And you'll notice that, okay, visually, in the interior of the coil, those magnetic field lines are very close together, suggesting the magnetic field is strong there. Okay, we say that is the number of loops, okay, or turns as it is generally called, increases, so does the magnetic field strength. A solenoid with 100 turns, for example, will have a magnetic field that is 100 times stronger than that of a single turn. Okay, but a solenoid with 200 turns would have a magnetic field strength in its interior that would be 200 times stronger than for a single turn. So you can see that by increasing the number of turns in the solenoid, very strong, okay, very powerful magnetic fields can be created. I asked the question, what happens to magnetic field strength inside the solenoid as the number of turns increases? As we said, okay, the magnetic field increases. So I will try to show you in the next slide, just demonstrate that the magnetic field on the interior of a solenoid is very, very strong. Okay, the magnetic field on the exterior of the solenoid is much, much weaker. Notice here in the figure that the magnetic field of that solenoid looks similar to that of a bar magnet, and it is true. The difference being, however, that with a lot of turns, you're going to be able to create a much more powerful magnetic field, okay, with magnetic field lines much closer together in the solenoid than you would be able to do in a typical bar magnet.
Now we're going to take a look at the magnetic field pattern inside and outside of a series of loops called a solenoid. So if we look here, we notice that the magnetic field of these compasses points in our north-south direction. We have no current inside of the solenoid at this time. But by taking a series of coils, we can generate a very powerful magnetic field on the interior of the coils. On the exterior, the magnetic field should be very weak. So let's notice what happens when we turn on the power source and generate a current in these coils. Here it goes. Okay, you see the very strong magnetic field generated in there. Okay, how quickly those compass needles move to align themselves with a very intense magnetic field inside the solenoid. So this is one of the functions of a solenoid. We use a solenoid to generate very strong magnetic fields in its interior. So how do we classify the magnetic properties of different materials? Well, we come up with a simple classification scheme for the magnetic properties of matter. We divide all matter into three classes, what we consider ferromagnetic materials, paramagnetic, and diamagnetic. And we'll look at some of the basic properties of each of these classes, starting with the ferromagnetic materials. Ferromagnetic materials, these are types of materials where the magnetic field of individual atoms is so strong that when they interact with neighboring atoms, they cause large clusters of them to line up with one another, creating magnetic fields that all point in the same directions. These clusters of aligned atoms are what we call magnetic domains, and we'll talk a little more about that in a bit. When a ferromagnetic material is placed in an external magnetic field, the magnetic domains become aligned with a field. And this domain alignment, it remains to some extent even after that field is removed. So as we'll see, you can create a permanent magnet by taking a ferromagnetic material and placing it in the magnetic field of a strong magnet. You can create a magnet out of it. So there aren't that many types of ferromagnetic materials: iron, nickel, and cobalt, just to name a few. Paramagnetic materials, these are type of materials where the magnetic field of individual atoms is not strong enough to bring magnetic fields of neighboring atoms into alignment. Thus, no magnetic domains are formed. When a paramagnetic material is placed in an external magnetic field, the magnetic fields of the individual atoms, they may become partially aligned with a field, but the alignment is relatively weak, so the magnetic attraction is hardly noticeable. And it turns out that when you remove that external field, the alignment of those atoms disappears. Paramagnetic materials are the most common class, and materials like aluminum, chromium, oxygen, sodium, most materials are paramagnetic. And you may know that if you take a piece of aluminum, for example, it's not attracted to a magnet. That when you bring a permanent magnet near it, you cannot permanently align the magnetic fields of the individual atoms of the aluminum. Or let's say if you do so, it's a very weak alignment. Diamagnetic materials form our third class. This is a type of material where neighboring atoms have electrons spinning in opposite directions, causing complete cancellation of atomic magnetic fields. Now, diamagnetic materials have this very interesting property that when they're placed in an external field, the speeds of orbiting electrons in neighboring atoms change unequally. This causes a net magnetic field in the opposite direction to the external field. This causes diamagnetic materials to be repelled by magnets. And as you saw with the superconductor demonstration previously, you saw that what we call the Magnus effect, where a superconductor was brought near a little tiny magnet, and that magnet levitated above it. So here we see diamagnetism in action. Other examples of diamagnetic materials include copper, lead, mercury, nitrogen gas, and water.
Let's talk briefly about the process of making a permanent magnet. We just mentioned that this certain class of materials called ferromagnetic materials have the ability to form magnetic domains. That is, to get large clusters of atoms to have their magnetic fields aligned in the same direction. So to make a magnet, we can take a piece of a ferromagnetic material, okay, like iron, and by placing it in a strong external magnetic field, we can cause the magnetic domains to come into alignment with that external magnetic field, thus making a magnet. Remember that, okay, for ferromagnetic materials, even when the external magnetic field is removed, the magnetic domains will remain in alignment, okay, to a great extent. So let's take a look at this magnetization process in greater detail to see how a piece of ferromagnetic material can become a permanent magnet. So we're going to take a look at a piece of iron in successive stages of magnetization. And in this first picture I'm showing you here, this represents an unmagnetized piece of iron. Each of the arrows you see in this picture represents a magnetic domain. And remember that a magnetic domain is a region in a ferromagnetic material consisting of millions of iron atoms, okay, that are in alignment, where the magnetic fields of those iron atoms are in alignment. You'll notice here that while the magnetic fields of the atoms within a given domain are aligned, notice in this picture that the domains themselves, okay, the magnetic fields of the domains themselves, which is what I'm representing here with these different arrows, are not in alignment. In which case, okay, there is no net magnetic field for this piece of iron. On average, you have about as many vectors pointing to the right as to the left, pointing up as down. So there is no net magnetic field when you add up all of those vectors together. Remember, we use a vector. It's a nice way to represent a magnet. You can think of the tip of the arrow as being a north pole and the tail of the arrow as being a south pole. Now, in this next picture I'm showing you, this is what happens when you place that unmagnetized piece of iron in an external magnetic field. As the external magnetic field is applied, the domains begin to come into alignment. And when you now compare picture 2 to picture 1, you'll notice that while the magnetic domains, those arrows don't all point in the same direction, on average, they tend to point, okay, more to the right than they do to the left. So this is what we would say when we think about properties of vectors. We would say, and we look at components, we would say, okay, this represents a slightly magnetized piece of iron because on average, those arrows tend to point more right than they do left. It turns out that if you actually were to use a stethoscope, okay, you know what doctors use to check out your heart and lungs, and you held a stethoscope near a piece of unmagnetized iron as that piece of iron was placed in an external magnetic field, you can actually hear those magnetic domains come into alignment. You'll hear this clickety-clack sound, okay, as they come into alignment. Okay, very, very cool thing to hear. So in the next picture I'm going to show you, this is a very fictitious picture that shows you a strongly, highly magnetized piece of iron. In this picture, you'll notice that all the magnetic domains point in the same direction, right? Each of those arrows, remember, represents a magnetic domain. And while a true piece of ferromagnetic material that is highly magnetized would never have the magnetic domains exactly in the same direction, okay, this kind of shows you the idea here of what's going on. So when all those magnetic domains, their fields are all in the same direction, you end up with a very strong magnetic field, a highly magnetized piece of iron. I want to show you here, okay, what happens, why it is that the poles of the magnet are at the ends of the magnet. Notice in the interior regions, what I'm showing you in red here, you'll notice here, let me get a laser pointer, that for every north pole in one domain, it's located near a south pole of another domain, and we get cancellation here. A north pole and a south pole will cancel each other out. But you'll notice that at the ends of the magnet here, there is no cancellation here for these arrows, okay, which suggests that you have a north pole at the end here, while here at the other end of the magnet, you'll notice these are all south poles from these domains. You get no domain cancellation. There is no cancellation of opposite poles, and that's why the poles of the magnet are at the ends of the magnet. The interior regions of the magnets, okay, as we said, the north poles in one domain get canceled by the south poles in the adjacent domain, and so on. Of course, there's a lot more domains than I'm actually showing you here. What I'd like to do is to show you another picture here, which maybe gives you a nicer feel for what's going on. You'll notice in this picture here, this is an unmagnetized piece of iron. You'll notice that domains are actually shown with these lines here, and you'll notice that within each domain, you see that the magnetic fields, all those arrows are in the same direction, showing that all the atoms in that domain have their magnetic fields in the same direction. Yet, you'll notice that any two adjacent domains, the directions of the magnetic fields, are not in the same direction. So this represents the unmagnetized piece of iron. This is kind of a better picture than what I'm showing you here, because I'm just showing you one arrow to represent a domain. Here you can see that the domains are represented by multiple arrows. But you'll notice in this picture over here, the highly magnetized piece of iron, that all of the arrows, not only within the domain, a given domain, are in alignment, but within all the domains, they all have the same direction, okay, which is what I'm showing you in this picture right here. We can see this with a real-time effect here. If each of these, the magnetic domains, is represented by a little tiny magnet with a north and south pole, you can see the effect of that external magnetic field is to bring those domains into alignment. So this animation nicely shows that. All right, so what happens when you subdivide a magnet? And many of you may know this, that when you break a magnet into two pieces, you actually get two equally strong magnets. Well, you kind of see here what's going on. That, as we said here, you still end up with domain cancellation in the interior region here, but the ends of that magnet represent the poles, okay, as before, so you end up with two equally strong magnets. Okay, in the region I'm showing you in red here we have we have pole cancellation, but at the ends, okay, even the broken end, you still have just as strong of a pole as you had before the break. And finally, we'll take a look at, what happens when if you want to ruin a magnet. Okay, if you heat a magnet or you bang a magnet repeatedly, you cause those magnetic domains to come out of alignment, okay, thus weakening the magnetic field. So in order to, keep a permanent magnet, to keep its magnetic field strong, like the way you bought it, not only do you have to store it properly, okay, but you've got to treat it right too. In time, too much banging causes the magnetic domains to come out of alignment. In this first demonstration, we'll talk about how to make a magnet by using a solenoid. This is very often the way that permanent magnets are created. That is, using an unmagnetized piece of a ferromagnetic material like iron and placing that unmagnetized piece of iron in the interior of a very powerful solenoid to cause the magnetic domains to come into alignment.
So what we're going to take a look at here is how to make a magnet with a piece of soft iron. Now if you look at the iron rod here, iron is special in that it has magnetic domains. But right now these magnetic domains are not aligned, meaning this piece of iron is not magnetic. And you'll notice that if I bring it near this compass, it really doesn't affect the compass because it's not yet a magnet. But what we're going to do is we're going to take this piece of soft iron and we're going to stick it on the interior of this solenoid. And you remember that a solenoid creates a very, very powerful magnetic field in its interior. So I'm going to place a current in the solenoid to create a powerful magnetic field, and when we do that, it will slowly bring these magnetic domains into alignment and create a magnet. So let's go ahead and start here. Okay, and we'll do this a few more times to ensure that we have okay. So we now take our piece of iron here, and by causing all those magnetic domains in there to be aligned, you see that we have turned it into a magnet. You can see how easily it interacts with the compass. Okay, remember the compass needle is just itself a tiny little magnet. Now if you want to ruin a magnet, if we take this piece of iron and we heat it up, or we bang it or drop it, we can cause those magnetic domains to once again come out of alignment.
This next demonstration again illustrates how a permanent magnet can be made by placing a piece of ferromagnetic material in an external magnetic field. Okay, but in this case, we're going to place that ferromagnetic material in a very weak magnetic field, and given enough time, okay, we will turn it into a magnet.
Now we've talked about making a magnet by taking a piece of iron and placing it in a magnetic field so that the magnetic domains in that piece of iron become aligned with the magnetic field. What I'm going to show you here is that the Earth's magnetic field, although very weak, can be used to create a magnet out of say a metal filing cabinet, or in this case I'm going to show you out of a steel door jamb. So if we think about it, this is a piece of steel. It contains iron. It has magnetic domains which do not start out in alignment. But because this steel door jamb exists in the very weak magnetic field of the Earth, over a long period of time and with continuous slamming of that door, we can gradually cause the magnetic domains to come into alignment. So I'm going to show you that by taking this device, which is we call it a magnet probe. It's basically a little compass that can rotate in 3 dimensions. And when I hold it near the door jamb here, you'll notice that the south pole of the magnet probe is oriented towards the door jamb. What I'm going to do is move this up very slowly and show you that the polarity will flip, showing you that where we may have a north pole down here, up at the top, the pole will change. So let me very slowly move it up, okay, and you will see that the polarity is starting to shift, okay, as the red end of the magnet probe is attracted. So you see up here at the top of this door jamb, we have a completely different magnetic pole than we do down at the bottom, suggesting that over time we've caused the magnetic domains of this steel door jamb to come into alignment to create a very weak magnet.